Hello, everybody. Welcome to Mankind in Training. I'm your host, Joshua Parr. Welcome back. I know it's been a while since I've done a video. Today is the Q&A episode. We have Patreon members and people who donated on the GoFundMe page to ask a question that I will answer on the air. In this video here, I picked the first 10. There is 4 more that I'm going to do in the next episode. So if you didn't see, if you paid and your question didn't get asked, it's one of the 4 that will start the next episode. I'm just waiting for a few more to add so I can do another one. So I noticed in these questions, now I did specify that I wanted science related questions, but it can vary throughout science. It doesn't necessarily, it seems like just about all of these are physics questions. And I am currently in college uh with a bachelor's for computer science and data science, but I do know quite a bit about physics, but I'm not a professional physicist yet, but I will do my best to try to answer these questions. And I'm going to bring up the Google machine so you guys know that I'm not just making things up. So without further ado, go here, zoom me up into here, like so. So our very first question I'm going to answer is Jared K. asks, what is the difference between protons, neutrons, and electrons? So these are the component parts of the atom. Now, there's quite a few differences between protons, neutrons, and electrons. The main one is charge. So a proton has a positive charge, an electron has a negative charge, and a neutron has a neutral charge. It doesn't have one. It's made of gluons. It kind of holds everything together. The fact that neutrons exist and electrons and protons in the fashion that they do resulted in the universe that you're currently existing in. So another thing that is a difference in them is the weight. Their weights vary. So let's cue this up here. What is the difference? In protons, neutrons, and it's wow. Apparently, this is a question that's been asked frequently. So, electrons are a type of subatomic particle with a negative charge. Protons are a type of subatomic particle with a positive charge. Protons are bound together in an atom's nucleus as a result of the strong nuclear force. Neutrons are a type of subatomic particle with no charge. They are neutral. And let's queue up something else to what are protons? So, protons are found in the nucleus of the atom and they reside together with the neutrons. The proton was discovered by Ernest Rutherford, who claimed that most of the space of an atom was empty and the mass was centered only in a small dense area within the atom called the nucleus. Protons are positively charged. The charge in this case is defined by the amount of Coulombic charge in an electron. The charge of the proton is the charge of the electron and therefore can be expressed as 1e 1.602 to the 10 to the negative 19th. The atomic nucleus remains positively charged due to the presence of protons. Protons are heavy and it has a mass of 1.672 times 10 to the negative 27 kilograms. As mentioned above, protons readily contribute the mass of the atom. Protons together with neutrons are called the nucleus. Hoping it would have some. And I was hoping it was going to say, anyway, it's relatively easy to Google machine the differences between these composite particles. And then, so a proton, that's something that's missing here. A proton is made with two up quarks and a down quark, and then a neutron is made with two down quarks and an up quark, I think is how that goes. There's another difference between them. So those larger particles are even made up of smaller subatomic particles. And that would be the difference. So back to the Google machine. Jared K., your question has been answered-ish. That is the main difference, the main differences between them. There's more, but we have other questions, and I will get to the next one. This is Madman725 asks, how many dimensions are there? Now, this is, you're probably going to be disappointed because we don't know. We know that for sure there are 3 spatial dimensions and 1 temporal dimension. For certain, because it's what we deal with every day. There's an X, Y, and Z axis, and then in that arena of X, Y, Z, things happen over time. And time isn't like a proper dimension, and that's why they say 3 plus 1 dimensions and don't add it, because they behave differently. A spatial dimension and a temporal dimension, I don't know that I can sufficiently answer this question. So the math worked out. Initially, the first people that started branching off from this, the first one was 5 dimensions. And Einstein really liked this idea. And then they kept working with it. And then the math for supersymmetry started to play out, where 10 dimensions, and then M theory says 11. And then bosonic string theory says 26 or 27, 26 plus 1. It's weird. We don't know how many dimensions there are. There could be an infinite amount of them. Like I said, just so you guys know that I'm not making this up. I'm going to Google each one of them. The world as we know it has 3 dimensions of space: length, width, and depth, like I was saying, and 1 dimension of time. But there's the mind-bending possibility that many more dimensions exist out there. According to string theory, one of the leading physics models of the last half century, the universe operates with 10 dimensions. And that's superstring theory. And then there's M theory. There's kind of a joke about nobody really knows what the M stands for. What's that guy's name? Witten, Edward Witten. And then bosonic string theory is 26 or 26 plus 1, or we don't know. We just don't know. So I'm sorry, Madman. We don't have a good answer for your question. Thank you for the donation, though, and the channel greatly appreciates it. So, Ukulele Lou asks, what is a Fourier transform and what does it do? So, the Fourier transform may be one of the single most important equations that we use regularly, and this is why. And then I'll ask separately the quantum version too. So a Fourier transform is a mathematical transform that decomposes functions into frequency components, which are represented by the output of the transform as a function of frequency over time. So it takes complicated things and smooths them out into a wave format based on the amplitude of the function itself. So Wikipedia's most common functions of time or space are transformed, which will output a function depending on temporal frequency or spatial frequency, respectively. That process is called analysis. An example of application would be decomposing the waveform of a musical chord into terms of the intensity of its constituent pitches. The term Fourier transform refers both to the frequency domain representation and the mathematical operation that associates the frequency domain representation to a function of time or space. The Fourier transform is a complex valued function representing the complex sinusoids that comprise the original function. For each frequency, the magnitude, absolute value, or the complex value represents the amplitude of a constituent complex sinusoid with that frequency. And the argument of the complex value represents that complex sinusoid's phase offset. If the frequency is not present, the transform has a value of 0 for that frequency. The Fourier transform is not limited to functions of time, but the domain of the original function is commonly referred to as the time domain. So this is constantly being used because we deal with waves a lot. And Fourier transforms make things easier to deal with mathematically. So back out. And we'll add to your question, even though you didn't ask this. In quantum computing, the quantum Fourier transform is a linear transformation on quantum bits and is the quantum analog of the discrete Fourier transform. The quantum Fourier transform is a part of many quantum algorithms, notably Shor's algorithm for factoring and computing the discrete logarithm, the quantum phase estimation algorithm for estimating eigenvalues of a unitary operator, and the algorithms for the hidden subgroup problem. The quantum Fourier transform was discovered by Don Coppersmith. The quantum Fourier transform can be performed efficiently on a quantum computer with decomposition into the product of simpler unitary matrices. So it's a decomposition. We had what did that say again? Don Coppersmith, and then I believe it was Joseph Fourier created the initial Fourier transform. Brilliant French mathematician Joseph Fourier, yeah, 1822. The analytic theory of heat. So there is the question for Ukulele Lou. Next we have triple or GGG. I shouldn't say triple G. GGG Barber Z asks, "What is dark matter? I'm still confused." We all are, buddy. Don't feel too bad, GGG barbers. Don't feel too bad. We we know dark matter has to exist in some form or another. It may not be. It just has to be there. There also dark energy. Both of those things have to be there. Anyway, what is dark matter? I'm so confused. That is a good one. Thank you for making me laugh. Because I am still confused too. Ah! Okay. Dark matter is a hypothetical form of matter thought to account for approximately 85% of the matter in the universe. The reason we think that is because when you look at a galaxy, say, and you watch it over time, and you calculate with where light allows us to see all the massive objects that interact with light in that galaxy. So we can make a rough estimate of what the mass would be in said galaxy. And the mass is way off. With what we can see, these spiral galaxies should tear themselves apart. Like, they shouldn't stay a spiral galaxy. All of their constituent parts should be spreading apart. They don't have the matter, the gravitational pull between these objects to hold itself together. It's not possible. So there literally has to be something. And here's where we get really confused. We have the standard model of particle physics. None of the things in the standard model of particle physics would account for the dark matter. Literally nothing at all. There is neutrinos or something like that, but they weigh nothing. There would have to be just a prodigious amount of them to make up the amount of mass that we're missing when we look into these galaxies. There has to be matter, and it has to be made of particles that do not interact pretty much at all, except for the weak force. That is the only one of the forces that it would have any like bearing that we understand. There has to be something. So axions was another idea of what it might be. Could be an axion, and that's a theoretical particle that they come up with. Now, different from dark matter is dark energy. And dark energy, and I don't like these terms because it's not properly dark, nor is it proper energy, but we see that there is a negative pressure, and that negative pressure is creating an anti-gravitational effect. It is pushing the galaxies away from each other faster than the speed of light. Nothing can travel faster than the speed of light, you say. You're right. But here's the thing. Nothing can travel faster than the speed of light through space. But space, it doesn't necessarily have that constraint. Space can do whatever it feels like doing. And this is where we get weird, because we can't see what space is shaped like. We have no idea what space is shaped like. We can only guess that it's curved, that it has some form of curvature to it. But then every time we try to calculate these things, it really seems like the universe is pretty flat, which is weird. It's very uniform and distributed, and it's flat. I recently seen a video on YouTube where a guy proposes that, and I had the same idea, so I really liked it, that there is a fourth physical dimension, not a temporal one. But instead of thinking it thinking of it like the X, Y, and Z axis. Think of it as enveloping all of the X, Y, and Z axis. Like the X, Y, and Z axis exist in this other dimension, which has a dynamic shape about it. And then anytime something that is massive in these three dimensions, it takes up space and it displaces the fourth dimension in such a way that the fourth dimension's affect is creating the gravity that we see, which would be a good explanation for why, because we know that gravity, we've been looking into that maybe gravity is a particle, and if so, can we find the gravitational field? We found gravitational waves. We've not yet found the gravitational particle, the graviton. So it might not be a particle at all. It might not be a force like the four forces that we're familiar with at all. It may not be. It might be something completely different. Dark matter is the hypothetical form of matter thought to account for approximately 85% of the matter in the universe. Dark matter is called dark because it does not appear to interact with the electromagnetic field, which means it does not absorb, reflect, or emit electromagnetic radiation, and is therefore difficult is an understatement. It's impossible to detect. It doesn't react with anything except for the weak force. So, and it might not interact with that. We just suspect that it probably would have to in order for things to pool in the way that they do. And the dark matter and dark energy seem to be very well distributed through the universe. Another great idea I heard recently is that the entire universe was at some point in time sucked into a black hole. And that's what the Big Bang was everything that was sucked into that black hole made it down to the singularity point, and then Hawking evaporation, Hawking radiation evaporated, and at when the black hole was no longer viable like as a black hole and it started to dissipate, everything that was in the singularity, and that's kind of what we have no idea why the universe is only 14 whatever billion year 13.6 billion years old. We don't know why. We don't know why there is an event horizon, if you will, because we can only see 13.6 billion years in all directions around us. And we, why? What is the reason for that? We have no idea. Everything got sucked into a black hole a long time ago. Makes pretty good sense of this. The dark matter and the dark energy could. So when we got sucked into this black hole, perhaps we were more dimensional as well. Perhaps this 3+1 is a result of being inside the black hole. Perhaps we had more dimensionality to our matter itself. So maybe when we were compressed, we were separated, if you will, from being able to interact with the old parts of what we were. But they're still there, and they're still massive, and but we have no way of interacting with them because they were like compressed, if you will. These are good ideas, and I enjoyed thinking about them. Good theories. We don't know what dark matter is, just that it does exist. And I know Wikipedia gets a bad rap. Don't hate on Wikipedia. If you're looking for something that is documented well to begin with, Wikipedia is going to have just as fine a documentation. It's not going to have a bunch of made up stuff. But if you don't necessarily, there's always more links. And if you ever have questions like these and you hit the Google machine and then it spits you out a bunch of lingo that you don't understand. They give you a bunch of scientific terminologies that you have to like okay, what's that word? What's this word? What the hell does that mean? And you have to look them up one by one, and it's a daunting task. So this is maybe a quicker way to get your question answered. I do answer questions on Quora as well for free. So you didn't have to pay necessarily for these. So there we are, barbers, GGG barbers. We're all still confused, but that's the best answer I'm going to be able to give you. We're not sure, and we're still looking. Cares Tuku 4. KRZ Tuku 4 asks, I'm sorry if I'm slaughtering you guys' names. I'm really bad at handles sometimes. I'm not sure what the yeah. Anyway, KRZ Tuku 4 asks, can we travel through wormholes? We don't know. No is the answer that you're gonna get from just about everybody. No. Just a straight up, they won't even consider it. Nope, we can't. That's a dumb idea. Just stop thinking about stuff. Stop thinking about science fiction things. It's not gonna work. We've discovered that well, we haven't discovered. This is something that Leonard Susskind has proposed. So, oh, and Maldacena, I think, was in on this too. ER equals EPR. Einstein-Rosen equals Einstein-Podolsky and Rosen. So let me see if I can get into that real quick. And then I will ask the actual question to Google. But this is something a little in depth. So ER equals EPR is a conjecture in physics stating that two entangled particles, a so-called Einstein-Podolsky-Rosen or EPR pair, are connected by a wormhole or an Einstein-Rosen bridge. This is thought by some to be a basis for unifying general relativity and quantum mechanics into a theory of everything. When they devised both of these things, they were completely separate, for sure. One was entanglement, and the other one was the proposition in general relativity of space-time being warped to, like, the best analogy is they take a sheet of paper and they have two dots and they're like, well, what's the shortest distance between the two dots? It's a straight line. Well, no, fold the paper in half and they're touching pretty much. Just have to make a little hole through space-time, if you will. So when they first thought of both of these things, no reason that they should be connected. No reason that they should be equivalent. That's for damn sure. That a wormhole is in fact so these particles, when they change state through time, or when they're so you entangle a particle and then you take it to the other side of the universe, and if you measure it, you know what the other particle is instantaneously. And they have to exchange this information, if you will, in some way or another. And that is what they're saying is happening here. There's a wormhole being created in the quantum realm between these two particles. So there's like the distance is an illusion, if you will. Once at the macroscopic world, distance is an illusion, because when you get down to the quantum world, it's not as you would suspect. So the conjecture was proposed by Susskind and Maldacena, like I was saying. They proposed that a wormhole, Einstein-Rosen bridge, is equivalent to a pair of maximally entangled black holes. EPR refers to quantum entanglement, EPR paradox. The symbol is derived from the first letters of the surnames of the authors. Conjectured resolution. This is a conjectured resolution to the AMPS firewall paradox. Whether or not there is a firewall depends upon what is thrown into the other distant black hole. However, as the firewall lies inside the event horizon, no external superluminal signaling would be possible. This conjecture is an extrapolation of the observation by Mark van Ramsdonk that a maximally extended ADS Schwarzschild black hole, anti-de Sitter space, which is a non-traversable wormhole. That's what ADS stands for. It was anti-de Sitter space. Sorry. A non-traversable wormhole is due to a pair of maximally entangled thermal conformal field theories via the ADS CFT correspondence. They backed up their conjecture by showing that the pair production of charged black holes in a background magnetic field leads to entangled black holes, but also after Wick rotation to a wormhole. Let's click on ADS CFT correspondence real quick. In theoretical physics, the anti-de Sitter conformal field theory correspondence, sometimes called Maldacena duality or gauge gravity duality, is a conjectured relationship between two kinds of physical theories. On one side are the anti-de Sitter spaces, which are used in theories of quantum gravity, formulated in terms of string theory or M theory. On the other side is the correspondence is the conformal field theories, which are quantum field theories, including theories similar to the Yang-Mills theories that describe elementary particles. So ADS CFT correspondence. And quickly, what was I going to do here? There was something I was going to be clicking on. Oh yeah, it was probably this. And then real quickly, anti-de Sitter space. An n-dimensional anti-de Sitter space, ADS sub n, is maximally symmetric Lorentzian manifold with constant negative scalar curvature. Anti-de Sitter space and de Sitter space are named after William de Sitter, professor of astronomy at Leiden University and director of the Leiden Observatory. William de Sitter and Albert Einstein worked together closely in Leiden in the 1920s on the space-time structure of the universe. Manifolds of constant curvature are most familiar in the case of two dimensions, where the elliptic plane or a surface of a sphere is a surface of a constant positive curvature. A Euclidean plane is a surface of a constant zero curvature, and a hyperbolic plane is a surface of a constant negative curvature. Einstein's general theory of relativity places space and time on equal footing so that one considers the geometry of a unified space-time instead of considering space and time separately. The cases of space-time of constant curvature are de Sitter space positive, Minkowski space 0, and the anti-de Sitter space negative. And they have to be one of these things. We think that the cosmological constant in the universe is slightly positive, but then we find that there has to be like there's a negative somewhere. So the anti-de Sitter space has to play some role in this. So Minkowski space-time, de Sitter space-time, and anti-de Sitter space-time. These are leaders in how to think of the manifold arena in which the universe plays. So back up to the Google machine to ask the question. I've kind of went on a tangent on this one because there's lots to learn to get you to the background. Can we travel through wormholes? Can we travel through wormholes? The entrances of general relativity wormholes are hidden behind event horizons, which are one-way barriers in space. That means if you were to enter the wormhole, you could never leave, which would defeat the purpose. The other problem is that they're ridiculously unstable. Okay, so to add to what the Google machine said, though, we have proven that it's possible with distributed negative energy to pass something from one side of the wormhole to the other. And I think that they did that with a quantum computer in the lab. They actually, uh, what's the best word to describe what happened there? But there was there's a qubit on a circuit, and they passed it through onto a different circuit without they used a wormhole, if you will, to get it from one to the other. But this was like an electron or something ridiculously small that they used with the qubit to put it through. So it's I don't know. I'm pretty sure that they figured out a way negative energy uh distributed in the wormhole itself could potentially allow something to travel from one side to the other. So that's not entirely correct, but yes. Yes, no. Just about everyone will say no. Just stop working on stuff like that. Just quit it. Quit being ridiculous. So I don't think your question is ridiculous, by the way. I'm just telling you what you're gonna hear uh most of the time, especially if you ask it on Quora. Those people are mean sometimes. I'm just curious. I have questions myself sometimes. Like I'll be watching a lecture and then I'm like, what? That doesn't make any sense. I thought it worked like this with this. And then I ask a question on Quora and they're like, what are you, a retard? Well, no, but I don't have a PhD in physics. So can you help me out, please? And not be a dick about it? It doesn't work like that. They're dicks about it. Anyway, I don't think your question was crazy, KRZ224, but I don't think it'll happen in your lifetime that will send anything bigger than a qubit through a wormhole and have it be surviving on the other side. The yes, maybe, probably not. Next, we have, and thank you again for all the questions, you guys. I know it's taken me forever to get through 5 of them. We're only halfway through. I wonder how long I've been doing this. Now, we have a different question. Queen Tess L42 asks, what is the difference between a matrix, a vector, and an array? Now this is the only question I think that I got out of the paid questions that wasn't necessarily physics related. This was the only one. And I want to repeat again for you guys who do want to participate in these question and answer episodes. It doesn't have to be physics at all. For one, I'm not a physicist. I do really really like quantum mechanics, and I've been trying my best to learn it as best as I can because I do want to work with quantum computers in the future too. Very much so. I would love to do R&D on quantum computers. That's really where I would like to be. But I'm currently in a bachelor's for computer science, data science, and like statistical mechanics type things. So it's I'm gonna have to do some either heavy certifications, or I'm gonna have to get a different bachelor's in quantum mechanics. I'm not sure. I need to talk to the people at the MIT's research. Uh, what was that guy's name that I was trying to get a hold of? I had sent him an email, and somebody from his staff had emailed me back. Uh, oh, I can't remember his name. Anyway, Queen Tess asked, what is the difference between a matrix, an array, and a vector? So a matrix is in brackets, and it is usually to denote anything. So it's hard to get you an example here. So typically, like when you see there will be individual elements in this matrix. And if it's a 3x3, there will be an element, 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 an element inside of parentheses. That is a matrix, a 3x3 matrix. If it was a 2x2 matrix, you'd shrink that up and it would go element, 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 element. An array, as I understand it, is a single. So there are columns and there are rows in the matrix. So an array is just a really, it's a one dimensional that way, but has how it's one dimension and has however many elements, and it's only the row. And then the vector is going to be only the column. It's going to be a one-dimensional with a bunch of different elements in it in a column arrangement, and then the array is going to be the row arrangement. Let's see if they have something different than what my understanding is, though. What is the difference between a matrix and array? An array and a vector. A matrix is a two-dimensional vector. An array is a vector with one or more dimensions. So an array with one dimension is almost the same as a vector. An array with two dimensions is almost the same as a matrix. Was hoping they'd have like some visual representations. Let's go to images. Maybe they'll have what I'm looking for. Kind of, yes. Okay. Here we are. I like that. Scalar factor. Everything is scaled by this. A vector is the column, like I was saying. A matrix is a 2x2 matrix right here. And then an array would just be just the top half of the matrix or the bottom half or whatever, but only in the row format. And then a tensor is this set of tuples that are arranged like that. And they don't have to be that size, obviously. They can be all sorts of different sizes. This is a feature vector. This is a feature matrix. And then that's an array. And then this is so this is how you transpose something. That's what that T is at the top corner. Just means to transpose it. The inverse version of that. But those are the differences between a matrix and a vector and an array, as I understand. You guys' questions can be about programming or even like life sciences. I don't mind looking up whatever and trying to make sense of it as best as I can for you. So there you go, Queen Tess. That is the difference. Next question. Archive. Archive asks, what is Gödel's incompleteness theorem? Good friggin' question. Good question. Thank you. Because like nobody knows what this is. I shouldn't say nobody, but for real, for what the actual importance of what he is saying, it it caught everybody out by surprise. And they had to take sickly Yodel into the giants of mathematics after this because it's brilliant. Yodel's incompleteness theorem says if you have a formulation of proving things in a mathematical language, I can always write you a question that is unprovable with your logic. There will always be a question that cannot be answered with this formulation. So math is incomplete. Nothing nothing can be like completely solved ever. What is Gödel's incompleteness theory? Oh, there's no E. Whoops. Whoops. Damn you, Bobby. There we go. Gödel's incompleteness theorems are two theorems of mathematical logic that are concerned with the limits of provability in formal axiomatic theories. These results, published by Kurt Gödel in 1931, are important both in mathematical logic and in the philosophy of mathematics. The theorems are widely but not universally interpreted as showing that Hilbert's program to find a complete and consistent set of axioms for all mathematics is impossible. The first incompleteness theorem states that no consistent system of axioms whose theorems can be listed by an effective procedure or an algorithm is capable of proving all truths about the arithmetic of natural numbers. For any such consistent formal system, there will always be statements about the natural numbers that are true, but are unprovable within the system. The second incompleteness theorem, an extension of the first, shows that the system cannot demonstrate its own consistency. Employing a diagonal argument, Gödel's incompleteness theorems were the first of several closely related theorems on limitations of formal systems. They were followed by Tarski's undefinability theorem on the formal undefinability of truth, and Church's proof that Hilbert's Entscheidungsproblem Entscheidungsproblem is unsolvable, and Turing's theorem that there is no algorithm to solve the halting problem. He, he basically poked holes in everything for everyone and said, listen, there's always something that is impossible to prove in your axioms, in your way of explaining things, in however which way you choose it. And then there's no way for you to prove your own consistency with your own math. That is what Gödel's incompleteness theorem is, and it's freaking brilliant. Great question. Who archive or archive, Hive. Lewis M asks, what is happening in the double slit experiment? So the one with electrons, they take and they have two slits, and they have another wall behind the wall with two slits in it. And this wall is the back wall is where the electrons land, and they're fired from a distributor one by one through the two slits. And what you'd expect to see in the physical world, you say you got a paintball gun and you're shooting a paintball gun through those two holes, you're going to see two bars where the holes are on the back wall of the paintballs that made it through, and they land, and it makes sense. There's two areas that big for the paintballs to have gone through. All the ones that hit the front wall didn't make it to the back wall. That makes sense. When you do this with electrons, and they did it with a stream at first, and they thought, well, they must be interacting with each other, and that's what's causing the interference. So they did them one by one and then added up the distribution at the end. And what they found is instead of these 2 bars, you will get 5 or 6 or 9, depending on how wide out the interference was. You will get a multiple amount of bars. So every place, it's weird. So they took a diagram and there's like a circular outcrop for every set of electrons or whatever. And then when you see the fields all overlap, any place where they cross, there will be another place a little bit down the trajectory where they cross as well. All of the crosses will line up. And so where those intersections are will lead you to one of those spots on the back wall where the interference pattern has frayed out to. And all the places that are just the curvature that don't have an intersection are the empty spots, the destructive part of the pattern. There's destructive and constructive interference, and that's what's happening in the double slit experiment. What happening in double slit? Single particles, such as photons, pass one at a time through a screen containing 2 slits. If either path is monitored, the photon seemingly passes through one slit or the other. No interference will be seen. That's the other part that I forgot to mention. So this is the big part that's super duper confusing. Is it a particle or is it a wave? When we do this, we get the interference pattern. When we try to measure it as it goes through the slits on its way to the wall, if we try to measure it, the wave function collapses and you get the 2 bars. Stop measuring it, the interference pattern comes back. Okay, this is a cool. Al Khalili, I like his version of this better, but he's okay. So what we're gonna do is we're gonna leave the camera there, but we're gonna sneak back and unplug it. So the photons can't know that they're being measured. Well, they have to know that they're being measured. Nothing's changed. The camera's still there. We unplug it and see what happens. The interference pattern, not the 2 bars, as you would expect. You get an interference pattern. But when you measure them, you get not an interference pattern. You get the 2 bars. This is called the measurement problem in quantum mechanics, and it is the biggest problem that we have that needs solved, if you will. That needs figured out what is actually happening here. Are the particles conscious? They almost have to have some level of understanding what's happening in the environment that they've been put in, or else they wouldn't be able to change state like that. It goes from being an interference pattern to you measure it, okay, it collapses. Okay, we turn the measurement apparatus off, but leave it right where it is, back to the interference pattern. The photons have to be, or the electrons, or whatever particle you use for this experiment, they have to be interacting with each other. And then a thought that I had was I maybe should read a little bit more into this, but if they're shooting the electrons and or photons one by one, but they leave them where they landed, as another one comes in, that electron hasn't like died. If it's still there on the board, it can, in fact, interact with something that's coming towards the same position that it's in as well. It has a wave function of its own, electromagnetic everything. Like its electromagnetic force could exactly distribute things as they're coming towards the sheet. But I don't know that that's what they did. They might have taken it one at a time. All right, redo the experiment. The electron's gone. The electrons, the thing with those is that, and photons too, they get absorbed. And it's like, so is it, the photoelectric effect is weird. But that's what's happening, is we don't know what's happening. We don't know why measurement collapses the wave function, or even if it does at all. But measurement has, and the reason I say that is because there's not like a mathematical operation for how that it does collapse the wave function. That is a big gap in our knowledge. We don't know what's happening there. It might not be collapsing the wave function. There might be something more fundamental going on that we're missing. But what is it? What is it that we could be missing? Thank you, or no, Lewis M. asked that one. That was Lewis M. Sabrina Witch, the teenage one, I'm assuming. 122 asks, what is the wave function and what does it do? Great question. Especially, and don't be scared to ask questions. Somebody will happily answer them for you. You don't have to go on Quora and get assaulted by people. Sorry I have so much hate on Quora, but man, so many mean people on there when you try to ask questions. Like, and questions that are good questions. If you didn't have some physics major explaining these things to you and you're trying to learn on your own just from reading things, you're gonna miss a lot. You're not gonna have the same educational, and then the big thing is like people with experience like that really like tell you what the big picture is, so you don't have to imagine it yourself. They kind of get you there, where I don't know. These questions, don't be scared to ask them. What is the wave function and what does it do? The wave function is how we've come to measure anything about the state of a particle and its harmonic oscillation of the particle over time. So there will be psi is the wave function's representor typically, and then psi is a function of x and t. X and then t being time. And that's your wave function. And it's incredibly important to quantum mechanics, to measuring anything, doing a Hamiltonian, doing Lagrangian mechanics. You need to know what the wave function is. So basically, what it do? Wave function psi, like I said, is a mathematical function that relates the location of an electron at a given point in space. It doesn't have to be an electron, I don't think. You can use the wave function to describe other subatomic particles as well. Not sure why it says electron, but at a given point in space identified by x, y, and z Cartesian coordinates to the amplitude of its wave, which corresponds to its energy. Thus, each wave function is associated with a particular energy state, E. They have it shaped like there's a well, and then there will be like its 0 point energy, like when it's at rest, that is the energy there. Everything is always in motion, so it can never be like at the bottom of the well there, but there will be a bare minimum amount of energy that particle can operate with, and that'll be its 0 point energy. And there is 0 point energy everywhere, even in empty space. Space is not empty at all. So I'm gonna skip down here real quick. So Erwin Schrödinger is like the main inventor, if you will, of the wave function. Schrödinger equation. is psi x and t. Where were we at here? Psi of x and t. Yeah, apparently we're not getting there. So anyway, Schrodinger is the first one who started, I guess. I shouldn't say first because it probably has a better history here. De Broglie and Erwin Schrödinger and others developed wave mechanics. Him and a few and so and Werner Heisenberg and Max Born, matrix mechanics. These were the two different approaches of doing quantum mechanical equations. And then Dirac, there was a problem with uh with Schrodinger's equation, a slight issue, if you will, and Paul Dirac made a great correction in order to fix the problem. A wave function in quantum physics is a mathematical description of the quantum state. These are quantum states. This is a oscillator, a spring with a ball on it, harmonic oscillator, classical one. Kx minus omega t. There's a complex number in there somewhere. The wave function is a complex valued probability amplitude, and the probabilities for the possible results of measurements made on the system can be derived from it. The most common symbols for a wave function are the Greek letters psi, respectively. The wave function is a function of the degrees of freedom corresponding to some maximal set of commuting observables. Once such representation is chosen, the wave function can be derived from a quantum state. For the given system, the choice of which commuting degrees of freedom is not to use is not unique, and correspondingly, the domain of the wave function is also not unique. For instance, it may be taken to be a function of all the position coordinates of all the particles over position of space for the momenta of the particles over momentum space. The two are related by a Fourier transform. We answered that earlier. Some particles, like electrons and photons, have non-zero spin, and the wave function for such particles includes spin as an intrinsic discrete degree of freedom. Other discrete variables can also be included, such as isospin. When a system has internal degrees of freedom, the wave function at each point in the continuous degrees of freedom assigns a complex number for each possible value of the discrete values of freedom. These are often displayed in a column matrix. All right, so what we should do here is let's go. Oh, go back to Google. Let's bring up standard model of particle physics. Damn it. No. I really just want that picture. Okay, anyway. So we have quarks we have leptons, and we have bosons. And the quarks are fermions. They have, I was trying to get, maybe I should have went to the wiki actually. The fermions have integer spin, and then leptons and bosons have half spins. Um, half integer spin, elementary fermions, elementary bosons with integer spin, force carriers, photon, WZ boson, and the Higgs boson is the only one with spin 0. Leptons and antileptons are half spin. They're electrons, muons, neutrinos. And these half. Apparently I had it backwards. I thought it was the other way around. Half spin quarks and antiquarks. Up, down, charm, strange, and the top and bottom quarks. Anyway, that is the wave function, and these are the standard model of particle physics. Now we're on to my last question for today. Anyway, like I said, if you are one of the 4 people that missed out on this episode, the next episode, you guys will be the first 4 questions. So thank you again for your donations. They're greatly appreciated. They will keep the channel rolling. Thank you guys. This is my last question of the day. Before we wrap this up, go back to all. Last question was Sabrina Witch 122. What is the wave function and what does it do? Thank you for your question. If you guys have any more questions, feel free to ask them. You don't, and even if you want to just send a message to the page, you don't have the money to pay for it, but you want your question answered, it's totally fine. I will answer whatever for whoever, for whatever reason. I kind of enjoyed these, so I'm glad I finally got enough questions to do an episode, because I've been waiting until I had at least 10 of them. And then finally I got like 6 of them last night, which put me over by 4. So Mia Love 86 asks, who was the most important contributor to quantum physics in your opinion? Wow. What a question. What a question. I'm going to go with the answer. So if you ask the same question to a lot of the giants of quantum mechanics, a lot of the giants of quantum mechanics will give you this same answer. Who is the most important contributor? And like, I want to say all of these giants' names, but all of these giants said the same thing. I got here on the shoulders of James Clerk Maxwell. And if you don't know who James Clerk Maxwell is, if you don't know now, you know. James Clerk Maxwell is electromagnetism. He has the most successful collection of understanding of the natural world that anybody had. Maxwell's equations literally lit the path for everybody else to figure out particle physics, figure out quantum mechanics. Niels Bohr and all of them they'd still be trying to figure out the electromagnetism portion of things. James Clerk Maxwell, I think, is the Einstein and you know, Schrodinger and Max Born and Werner Heisenberg and Niels Bohr, all of them will tell you that they are where they are because of James Clerk Maxwell. So when you ask the giants that I probably should have named for who had the most contribution to quantum mechanics, those people say it's James Clerk Maxwell and his equations for electromagnetism. The strong and the weak nuclear force, the forces, as we know them, were discovered in their most accurate form to date, James Clerk Maxwell and his equations. I was hoping we'd get a little. They don't seem to actually have the equation portions in here, unfortunately. Don't have any of the actual equations here, but this is the answer I'm giving because that's what the giants themselves say. Now, for a close second, third, and fourth and fifth places, we have obviously everybody knows Albert Einstein, and he's on this list. The photoelectric effect and his work in special and general relativity have, at the very least, got the world in the science community to these people all got together in the early 1900s and late 1800s and have developed all of the developing of quantum theory happened in a span of like 60 years. All of the major foundational breakthroughs all happened during these guys' lifetimes. And so James Clerk Maxwell and Sir Isaac Newton obviously is a giant too. But so nextly, Einstein is on this list, but who I'm going to talk about next as the other giant, the most important contributor to quantum physics. This will probably this will probably surprise you. I've heard this stated by a lot of people, though, that the smartest person in the last 250 years to have graced the planet Earth is this man right here, John von Neumann. So this is a quote that I heard. There's John von Neumann, and then there's the rest of us. He had such an unparalleled understanding of everything science, and he has the most massive contribution to, I'm not just going to say quantum mechanics, all science. This guy has von Neumann this, von Neumann that, von Neumann. Okay, so selected works, or what's the see also page, probably got just an outrageous amount of things. Okay, I thought I had seen a list of like all the different things that had John von Neumann's name, and it was ridiculous. Okay, yeah, right here. Known for. Oh no, this isn't it either. Known for abelian von Neumann algebra, affiliated operator, almost periodic functions on locally compact abelian group, alternating projection method, amenable groups, arithmetic logic unit, the ALU that's in your computer. John von Neumann invented that. Artificial life, artificial viscosity, the axiom of regularity, the axiom of limitation of size, backward induction, Birkhoff von Neumann algorithm, Birkhoff von Neumann theorem, blast wave fluid dynamics, Taylor von Neumann set-off blast wave, the bounded set, the topological vector space, Calkin correspondence, It goes on 93 more. Quantum mechanics, 93 more. It's this list of all the things that this man has contributed to science is probably the longest out of anybody that I can think of. He had more. So James Clerk Maxwell, number one, John von Neumann, number two, as probably the most important. And I'm just saying to science, period, along with quantum mechanics. He obviously had a ton of quantum mechanics stuff too. 93 different contributions to quantum mechanics along with all the other science. So nextly, we have to include Erwin Schrödinger because of the wave function. Erwin Schrödinger is my number three because we still are using the wave function to this day to describe the wave function is everything. I'm going to go ahead and say that like you and me and everybody else that is alive right now is entangled together in a single wave function that distributes throughout the entire universe. And we can't leave it. We are in this wave function. We are trapped within the wave function and you cannot escape it. And everything that you encounter on a daily basis is behavioral waves interacting with other waves. And so I think there's something more fundamental going on than wave function collapse, like I was saying. There's the wave function is everything really, and we have to give Schrodinger his due, and his umlaut. We have to give poor Erwin his umlaut. I heard Stephen Wolfram say that during Schrodinger has an umlaut on the O in Schrodinger. Nextly, so Schrodinger had his equation fixed by Paul Dirac. Paul Dirac is another giant in the field. And then nextly after Paul Dirac, we have to go Richard Feynman. Quantum electrodynamics, Feynman diagrams. And then Albert Einstein. Like I said, general relativity, special relativity, the photoelectric effect, just his brilliant mind influencing other people's brilliant minds. And the we are reaping the benefits still today of things that Albert Einstein has said and helped work on. Nextly, after those guys, everyone says, I shouldn't say everyone, a lot of people say Stephen Hawking is overrated and he's really not that brilliant. And if it wasn't for his disease, he wouldn't have been as important and he didn't really contribute a whole lot to the. I disagree because when it comes to like gravitational lensing and black holes, and he really dove in, dark matter, he really dove into the hardest to understand things and tried to figure them out. And we still have a bunch of like successful algorithms that Stephen Hawking, we can't disprove them. They probably are correct-ish. They probably work. They probably do describe what happens inside of a black hole beyond the event horizon, or at least the mathematics to something as it's being pulled into a black hole. And then the holographic principle has taught us a ton of things recently. So to just say Stephen Hawking was overrated and hasn't contributed anything is ridiculous. He's contributed quite a bit. And then after our good friend Stephen Hawking, we have today's people that are still working for us, you know. We have the names that I like to listen to on what they have to say about the world. Leonard Susskind is pretty brilliant most of the time. I like Brian Greene. I like Brian Cox. And I like what's Sean Carroll. I really like Sean Carroll too. I think he's quite brilliant. And then there's Gates. Jim Gates is another person who's brilliant and working on it today. Michio Kaku is a excellent pundit for science these days. String theory. We have a lot of giants. We have a lot of them. Stephen Wolfram, like I was his way of going about hypergraph and giving it degrees of freedom and watching systems evolve in a graphical format, the geometry of the universe. I like it. I like it a lot. Thank you guys. Thank you everybody for your questions and for the money for paying to have your questions answered. I appreciate all the donations. I do. Jared K, Madman 725, Ukulele Lou, GGG Barber Z, KRZ Tuku 4, Queen Tess L42, Hoo Hoo Archive, Lewis M, Sabrina Witch 122, Mia Love 86. Thank you, all of you. I appreciate the money, the donations. I love it. You'll keep the channel rolling. Anybody else who has a question, science or I'm just gonna. It doesn't have to be science even. I'll just answer questions. Period. You can just ask me questions. I'm fine with that. We can spread this out a little bit further. I was surprised to have gotten like entirely quantum mechanics questions. Like I said, I'm not a professional physicist yet, but I'm working on it. That is a great interest of mine, and I probably am an okay person to answer these questions, even though I don't have a degree. And like I said, I implemented the Google machine, so you guys knew I wasn't just making things up to answer your questions. Computer science, coding questions are totally, that's what I was mostly expecting to get, but I'm not angry by any means about the quantum mechanics questions. I do love talking about it, so go ahead and ask those too. But for the next Q&A, I'll take, yeah, I'll take anything. Thank you guys, and thank you for watching. This has been another episode of Mankind in Training. I appreciate it greatly. See you guys on the next one.